So I'm very pleased to introduce the third speaker of this afternoon, Xavier Leroy, who's a senior researcher at INRIA Rocancourt, where he leads the gallium team. So Xavier is famous for his work on camel in the 90s, and about 10 years ago, in 2004, he started the CompCert project, whose purpose is to write a compiler, a C compiler, inside the CoC proof assistant. And so it's a perfect illustration of the idea of building certified machine-checked programs using proof assistant like CoC. So we are very happy to have him today, and he'll speak about his work now.
Thank you. So thank you for the invitation. I'm very glad to talk here today, especially since I took lectures in this room about 25 years ago. So it's interesting to see what it looks like from the bottom. So actually today I'm going to talk about proof assistance in computer science research, and through three examples. Only one will be this CompCert project. But before, let me say a few words about the relationships between mathematics and computer science, and especially the complicated relationship that computer scientists have with mathematical proof. So, of course, there are many areas of computer science that are deeply rooted in mathematics. Well, for numerical analysis, it's obviously all about differential equations, but perhaps less obviously, if you're doing analysis of algorithms, average case, then you need to study the combinatorial structure of the problem, and then through the generating series, you end up doing complex analysis. If you're into network performance, well, network protocols and performance analysis, then you're going to do a lot of probabilities, like Markov processes and the like. Machine learning, which is a hot topic in the last 5 years, well, it succeeds where artificial intelligence failed in the 80s, because machine learning is strongly grounded in statistics. Cryptography uses lots of mathematics, like number theory, elliptic curves, and semantics of programming languages, which is an important topic of this trimester, where it picks ideas from a lot of ideas from mathematics, mathematical logic, category theory, and a hodgepodge of other mathematical formalisms. And so mathematical models and proofs are essential in many areas of computer science for validation. Good luck getting a paper accepted on one of those topics without appropriate mathematical justifications. And even for discovery of new ideas, new algorithms, new protocols, etc. At the same time, well, computer science is applied mathematics, but it's also engineering. And there's a constant tension between the two, and in particular a temptation, okay, of making things that are applicable to the greater world, okay? Computing as it exists today, something that can get out of the lab. I mean, if you're doing network protocols or network security, it's more rewarding if you can fortify the internet a little bit, rather than working on your own protocols that nobody's using. And likewise, when you're into programming languages and tools like I am, it's of course more satisfying when you're working on a language that has millions of lines of code already written. And so this causes a tension between, on the one hand, elegant and cluttered abstractions, and on the other hand, more practical-oriented formalizations, but that tend to be overly detailed and messy. And when it comes to proofs, there's also a tension. We start with cute little proofs, certainly not mathematical monuments like we saw in the first two talks, but, well, decent things that can be published. And we end up with either excruciatingly long, like 40 pages, and every lemma has 20 cases, or fast and loose proofs. You know, well, here are 2 cases, the remaining 18 are similar. And as John Mitchell said, well, proofs written by computer scientists are boring, because they read as if the author is programming the reader. But that's the point, okay? Who said that the reader must be human? And that's what the proof assistant community has been telling us for the last 40 years or so, that proofs can, and maybe even should, be checked by computers. So, and so that sounds like a perfect opportunity to take those proof assistants for a spin, okay, and apply them to contemporary problems in computer science. Not just constructing the reals for the 10th time. And so this is the purpose of this talk. So that will be 3 short stories about uses of proof assistants that enables computer science research to scale to in unprecedented ways. And so my first example will be on programming languages and formalization and metatheory. And the second is on deductive verification of critical software. And the third will be on my own work on the CompCert formally verified compiler. So let me start with formalizing a programming language. So what does it mean to make it mathematically unambiguous? Well, you have to define the syntax. What do programs look like? You have to define dynamic semantics, how programs execute, what do they compute, what computation do they denote. And then, in most languages, there's a type system or some other form of static semantics that defines programs that are well-formed and safe. And so here is what it looks like for a very, very simplified language, the so-called simply type lambda calculus. So most of you have seen that 100 times already. And for the others, I just want you, the message I want you to take back home is that the specification is quite small. Okay, it fits on one slide, it fits easily in your head, and there's only 1, 2, 3, 4 rules to define what it means for a term to be well-formed and have a given type. All right? And so based on this definition, you can then do so-called metatheoretic work, which is a pretentious word to just mean valuable theorems that hold for all well-typed programs, not just one program in particular, but all of them that are well-typed. Typically type soundness, execution never crashes on an undefined computation, like applying an integer as if it were a function, or normalization. All executions terminate. And there are also algorithmic issues related to type checking, like decidability. But nobody is really interested in the lambda calculus, in the simply type lambda calculus, only for pedagogical reason. Okay, it's just too weak to program into. So progressively, people have been looking at more and more complicated type systems, and so here is an example from the 90s, Fsub, which tries to, which has support for polymorphic and subtyping, which are 2 important features of object-oriented languages. Okay, and again, I'm not going through all those rules, but just to notice that there are more. Okay, and in particular, the subtyping rule that says, for instance, if you have a term that of type natural number, it can be used in any context expecting a rational, for instance. And it's not over. There are some additional rules that define subtyping between compound types, pretty much like set inclusion between function spaces. All right, so that's more complicated to present, and the metatheory is a lot harder. And there are some surprises. For instance, after a couple of years, it was realized by Benjamin Pierce that type checking is undecidable for this full Fsub calculus, because basically you can encode the halting problem for some kind of Turing machine just in those silly little rules. And even though for a closely related and only slightly more restricted version of Fsub called kernel Fsub, type checking is easily decidable. So that's the kind of surprises you get. But of course, it's not over. Okay, there are so many type systems to explore. You want to type more features, imperative features, object orientation, concurrency distribution. You want to type them more precisely with other forms of polymorphism, of type abstraction, of refinement types, of dependent types. And then you also want to type check not just source languages, but maybe intermediate languages or machine languages. And so that results in hundreds of papers with mechanized metatheory proofs that become intractable quite quickly, okay, just because the case analyses are too large and those kind of things. And eventually the patience of reviewers is exhausted. So, and it's not over yet, okay? The Grail is a formalization of real-world programming languages, and that's been done very, well, not very often because it's such a major undertaking. So here are 2 examples for standard ML and for Java. And these are book-sized, literally. There are hundreds of inference rules, and very little can be proved about them. So that was the situation around 2005 when some some researchers from University of Pennsylvania decided to start the POPL challenge. So POPL is Principles of Programming Languages. That's a major conference in this area of work. And so their statement of the challenge starts with a manifesto. How close are we to a world where every paper on programming languages is accompanied by an electronic appendix with machine-checked proofs? And to try to assess how far we are from this point, or how close we are, they set up a challenge, which is to mechanize the metatheory of Fsub, the second system I showed, in the proof assistant of your choice. And the community rose to the challenge. There was about 15 solutions submitted, more or less complete, using 7 different proof assistants. And well, there was some good news and there was some bad news. So the good news is that all solutions handle part 1 of the challenge, which is the most difficult proof in all the metatheory of Fsub, is proving that subtyping is transitive according to those rules. Well, it better has to be transitive, okay, morally set inclusion. And the proof is a little bit subtle. You need to do an induction and the size of the middle term. Any other induction will not work. And you have to prove at the same time a more, by simultaneous induction, a more technical property called narrowing. But so the good thing is that all the 15 solutions were able to complete that proof, and in most of them, the mechanized proofs are not much bigger than a detailed pencil and paper proof. So success? Well, not quite. The bad news is that all solutions have a hard time dealing with something that looks pretty trivial, which is variable bindings and invariance by renaming of bound variables, which is called alpha equivalence in the business. And so for those of you who are not familiar, well, here are some mathematical notations, familiar mathematical notations, okay, quantifiers, universal quantifier, a big sum, an integral, a function definition. And we know that in all those cases, the x variable here, the I variable here, the x and the x, are just conventional, okay? We could very well rename them, use a different name, and that would mean the same thing, okay? X becomes Y, I become J, X becomes T, X becomes Z, still works, but watch out. If X becomes E, then you've changed the name of the meaning of your function, right? Because you've captured this constant E. So, but with this little caveat, okay, all mathematicians never get into problems with that, okay? It's just probably hardwired in our brain that we can do alpha conversion correctly. But not in the brain of proof assistants by far. And actually, the 15 solutions, there were so many that because they explored a great many different ways of dealing with alpha conversion and bound variables. And so some of them used special support in the logic itself and in the proof assistant, like nominal logic by Andy Pitts, which is really putting the notion of names and renamings inside your logic and your logical formulas. Or higher order abstract syntax in 12 metatheory, which is a very nice encoding, but has some limitation. I mean, to avoid contradictions and paradoxes, you have to restrict the expressiveness of functions very, very much. And other solutions were using concrete encodings, you know, special representation of terms, so canonical representation, so that alpha equivalence is equality. The most famous is the Breen indices, introduced by Nikolai de Breen for Automath, the very first proof assistant that was mentioned earlier, and some other variants. And there's no best approach yet. And because of the need to use definition statements, to use those kind of encodings and so on, definitions and statements do not look exactly like on paper, which is a bit of a concern sometimes. But still, despite this difficulty, in parallel with POPL and following POPL, there was several successful projects to mechanize large real-world programming languages. For instance, Java and its virtual machine at Munich, in Isabelle HOL, Standard ML at CMU in 12, various formalizations of C in HOL in Koch, JavaScript, more recently at Imperial College and INRIA, and even x86 machine language, the language of the microprocessor of your MacBook, at various places. And so those formalizations are not necessarily very pretty, because these are not pretty languages like C or JavaScript, but well, these are the languages that power embedded systems and the web respectively, so it has to be done. And those formalizations are usable and actually used to prove specific programs, to prove program transformations, and to prove some more general metatheoretic results. And we will see two examples very shortly. And as another point of measure of success, perhaps, is that nowadays about 15% of POPL submissions come with a machine-checked proof. All right, so speaking of program proof, let me tell you a few words about that. and let me start with, well, the observation that there is software and then there is critical software. So the ordinary software, that's everything that runs on your PC, on your smartphone, that powers the administrative services of your institution. And, well, it's awfully buggy, of course, but, well, it causes frustration, it causes loss of time, it causes frequent upgrades, but life goes on. One notch above, there's the sensitive software, where problems can cause loss of money, big loss of money, bad public relation, or even liability issues, like getting sued. And that is typically everything having to do with security, security of data, security of networks, privacy on the internet, this famous Heartbleed attack that was already mentioned, which is causing all sorts of cold sweats to that many people. But that's not the worst. Okay? The worst is critical software. When something goes wrong, someone dies. And all of the below, of course. And you can find that, for instance, in railways, driverless metros, in medical equipment like pacemakers, in control of chemical or nuclear plants, in airplanes, fly-by-wire systems, etc. And so clearly, critical software is not developed and validated like more ordinary software. But still, the dominant approach, even today in industry, is testing. So extremely careful and intensive testing. And, well, as Dijkstra said in a famous quote, program testing can be used to show the presence of bugs, but never to show their absence. That was maybe a little too strong of him. And at any rate, there's an alternative that is on the rise, which is tool-assisted formal verification, which is basically trying to verify and possibly infer properties that will hold of all possible executions of a program. And that is starting to be used in some industrial contexts, like the airplane industry, the railway industry, for various reasons. One is to obtain independent guarantees besides testing. Those people love it when something is true for two completely different and independent reasons. Okay, that makes it truer. Possibly to obtain stronger guarantees than can be obtained by testing, although these industrial people will never admit that their testing is inadequate. Okay, never admit. And also, perhaps to save time and money, because rigorous testing can be extremely expensive. So here's a little panorama of verification tools. So it's organized in basically two axes. One is whether it's automatic, push button, or requires significant user intervention. And that is kind of correlated with how big a piece of software can be verified in reasonable time. And the other axis is the kind of the expressiveness, how strong are and varied are the properties that can be checked. So at the very automatic part, there's static analysis, where it's only going to infer some very simple properties, like, I don't know, linear inequalities between integer variables, but that's enough to establish some basic safety properties, like no access outside of the bounds of an array. And the Heartbleed attack is an access outside of the bounds of an array, okay? And so you can think of static analyzers. There are also model checkers that are very specialized towards reachability properties. Can I reach this state? You can see them as very specialized logics with very specialized and efficient automatic provers. Then, going to the right of this diagram, there's deductive program provers, things like Hoare logic, where you can express quite a few properties up to full correctness using first-order logic. And then that will be checked by automatic theorem provers in first-order logic. And so proof assistants are very much to the right of this diagram. Then they give you enormous power in the logic, like higher order logic, and especially induction, ability to reason and inductive data structures, for instance. But they require a lot of interaction and help and hand-holding by the user. So this is a little abstract, so let me show you a concrete example. The example is from Knuth, The Art of Computer Programming, Volume 1. And it's about computing the first n prime numbers. So in Knuth, it's written in assembly. Here, I wrote it in pseudo Java, but the algorithm is trivial. You try successive odd numbers m, and you strike out those that are divisible by primes you already found. OK? So if you give that to a static analyzer, it can probably infer that I is between 1 and n, and j between 0 and I inside the loop. And hence, array excesses are safe, okay, are within bounds. That's already good to know. Now, if you use an automatic program prover, it can prove partial correctness, provided the user gives detailed loop invariance. So this is a plausible invariant for the inside loop. That says basically that in the array A between 0 and I, there's exactly the same prime numbers as in the interval 2 to m. And the user also has to give some axioms about primality and divisibility. And termination won't be proved in general because it depends on the fact that there is no greatest prime number. Okay, and that's not completely obvious to how to tell that to an automatic theorem prover in a way it can exploit. Okay, but that's not Knuth's code. Okay, Knuth's code has an optimization, which is that this test, j less than I, is redundant. And so Knuth doesn't do it and asks in an exercise, why? And the answer is because of Bertrand's postulate, which is a non-trivial result in the distribution of prime numbers, which was proved by Chebyshev and later reproved by Erdős. And it says that for all positive n, the interval n to 2n contains at least one prime number. Okay. And if you really want to prove that, well, that's a lot of work. And actually, while preparing these slides, I discovered that Laurent Théry, a colleague from INRIA Sofia, did this proof in Coq in 2002. But, well, that's non-trivial. OK, so that was an example of a small-scale deductive verification of a program. Now let's move to a much larger scale, which is the verification of the core of an operating system. So that's the SEL4 project at NICTA in Australia, led by Gervin Klein. And so basically what is a microkernel? Well, you may know what is a kernel, monolithic kernel for an operating system is really a big pile of code, like the 10 million lines of code, that sits on top of the hardware and mediates access to hardware resources towards the applications. So applications are pretty much shielded from one another, okay? In particular, if one is malicious or buggy, it cannot too much affect the other one. But the kernel can do anything, and it's so big that it is buggy, of course. So the microkernel approach is to keep only the core access control facilities. Okay, it's about 1,000 times smaller, and push all other operating system services to the protected space, where at least they cannot interfere too much with one another. And so, and then the microkernel becomes almost small enough for verification. And that's exactly what they did at NICTA. So they started with a prototype of the operating system, executable prototype written in the Haskell pure functional language. And that served as a blueprint for many things, as you will see. And then in parallel, well, one group developed an optimized C implementation of the kernel. Okay, these are systems people, they really shave cycles and so on. And another group started to write high-level abstract specifications in the Isabelle HOL prover. And then, well, from the Haskell prototype, they had a tool that automatically generated low-level executable specs, still in Isabelle HOL, and another tool that extracted the semantics of the C implementation using one of those formalizations of C I mentioned earlier. And then they were able to complete a refinement proof in 2 steps. So refinement means basically that any action of the low level is justified, is one possible action according to the high level. So there are 2 steps of refinement, from high level to low level specs, and that was done manually, interactively with the tool, and from low level specs to the actual C code, which was automated to a large extent. So that's really an amazing, oh yeah, and it's not over. And then once they've done all that, they also moved towards proving generic security properties that are true for all programs that run on top of this interface. And so it's a really amazing milestone. Well, first of all, it's a dream come true. Okay, since the late 70s, there have been about 15 attempts at verifying operating systems, and all were unsuccessful. And it's particularly remarkable because they made no compromise on the performance of the operating system, which is about 80% of the speed of the fastest unverified L4-style kernel available, so totally competitive. And it's probably the largest deductive verification of a software system ever done. It's about 20 person-years to 200,000 lines of proofs at least. And it's really amazing that they were able to pull it off. Okay, and so how am I doing with time? Fine? Okay. Excellent. So let me move to my last short story, which is about formally verified compilation. And it's actually related to those wonderful verification tools I mentioned earlier, barrel checkers, program provers, static analyzers. Because when industrial people like Airbus or Rockwell Collins use those tools, and they do use them, well, there are issues of trust and how much confidence we can have in the results of those tools that at the moment certainly prevent them from totally replacing tests in a number of situations. So there are 2 risks here. The obvious risk is the unsoundness of the static analysis tool. Maybe the tool is saying, okay, everything is fine, but actually missed one possible case of failure because perhaps it didn't follow all execution passes, okay? So are verification tools semantically sound? That's a tough question. And then comes question number 2, which is that in a few cases what is analyzed or verified is the actual executable machine code that runs in the airplane. But more often than not, it's a form of source code, maybe C source code, or even an executable model like written in Simulink or Skate. And the actual executable is actually generated from those higher level languages through code generation or compilation, okay? And so the risk here is miscompilation. A bug in the compiler could cause it to generate wrong executable code from a correct source program that's been formally verified, okay? And that's unpleasant. That's very well documented. So there are some examples of some reports on miscompilation. For instance, on the way integer division is compiled by some compilers. In '95, about 12 out of 20 got it wrong. In 2008, ID and Reger at University of Utah tested another delicate aspect of C, which is access to volatile memory, and again found bugs in the 13 compilers they tested. And a few years later, the same team at Utah generalized their testing method based on random testing, and again found lots of bugs in lots of compilers. And every compiler they tested was found to silently generate wrong code when presented with valid input. Okay. So why is it so hard to get a compiler right? Okay. Well, that's because compilers actually do pretty subtle things with the programs you give to them, trying to increase their performance and take best advantage of the hardware. And so here is an example of optimizing compilation that I did about 10 years ago when I started this CompCert project. So this is a little bit of C code that implements dot product between 2 vectors of double precision floating point numbers. So the code is about as stupid as you can imagine. It's just a transliteration of the mathematical definition with a big sigma. And so then I compiled it with a good optimizing compiler at the time and looked at the generated assembly code, and it was very long and it made absolutely no sense at all. But maybe that's because it was assembly code. So then I spent another 30 minutes manually decompiling this code back to C code, okay, and I got this, which you probably can't read, but even if you could, it would still make no sense. And after staring at that for a while, you observe a loop that might correspond to the original loop, except that the compiler chose to unroll the original loop by a factor of 4. So every iteration of this loop does the work of 4 iterations of the initial loop. Then it applied a technique known as software pipelining, whereas at each iteration of this big loop, you're computing the additions for the current iteration, the multiplications for the next iteration, and the memory accesses, the 8 loads for the next iteration. Why? Because it gives more time to the hardware to actually compute all those results. Okay, it increases instruction level parallelism. Okay, wonderful. And then what does everything else do? All the other code here does? Well, it's just special cases. Because pipelines, well, the first iteration of a pipeline is special. The pipeline needs to be filled, to be primed, sorry, to be initialized. Then the last iteration is special. It needs to be drained. Then if the number of iterations is too small, the pipeline doesn't apply. So you need to fall back to regular sequential code. And then if the number of iterations n is not a multiple of 4, okay, you also need some other kind of compensation code. So in the end, the result is that this code runs maybe twice as fast as a naive assembly code you could have written by hand. That's wonderful. But does it still compute dot product? So how to address miscompilation? Well, there are some best industrial practices, like even more testing, some manual reviews of generated assembly code and representative program fragments, turning some optimizations off, etc., etc. So that keeps the problem under control, but doesn't solve it. And there's, of course, a more radical solution, which is to formally verify the compiler itself. After all, the compiler is a program like any others. And unlike an operating system, it has a pretty simple specification, which is that if compilation succeeds, the generated code should behave as prescribed by the semantics of the source program. Okay? So it's just a semantic preservation property through compilation. And a corollary of this theorem is that any safety property of the observable behavior of the source program that, for instance, you've proved, or using program proof or static analysis or whatever at the source level, will carry over automatically to the generated executable code, the one that actually runs. So this is good, and actually it's a very old idea. The first paper that said, oh, there might be something interesting to prove about compiler goes back to 1967 by McCarthy and Painter. So they started small, just compiling arithmetic expressions, kind of the simplest language you can think of, down to stack machine code. But they said, OK, it's a prototype for the more complicated task of proving the correctness of usable compilers. And only 5 years later, Robin Milner and Richard Weyrauch mechanized the proof of McCarthy and Painter using one of the very first proof assistants, the Stanford LCF proof assistant. So again, they only do arithmetic expressions, but they say that they anticipate no difficulty with the remainder, I mean, scaling to more features. So that was a little bit optimistic, and actually it took a while to scale, and that's precisely what I've been working on for the last 10 years with some colleagues, especially Sandrine Blazy, who's now at University of Rennes. So the goal of this project is to develop and prove correct a realistic compiler that can be used for critical embedded software. So it means that, well, we can't just compile arithmetic expressions. We need to compile a language that is used in this context. So this is a very large subset of the C language in all its ugliness. Likewise, the target language, well, that's assembly for processors that are actually used in critical embedded systems, PowerPC, ARM, and x86. And we try to generate reasonably compact and fast code through careful code generation and a few optimizations. So clearly, we're not trying to prove an existing compiler. That's probably very hard because those haven't been written with the needs of a proof in mind. We're writing the compiler from scratch and doing its proof of correctness at the same time. So this is the formally verified part of the compiler. So as most compilers, it's a pipeline of successive passes, successive transformations. So we start with CompCert C, our subset of the C language, then go through a number of intermediate languages in blue of progressively lower semantic level, and end up with assembly language for our 3 targets. And so every arrow is a pass, a compilation pass, a program transformation. So some of them just re-express high-level constructs in terms of lower-level constructs, and some of them are optimizations, try to improve the performance of the code. So that may look complicated. From a compilation standpoint, it's kind of trivial. Okay, real compilers are a lot more complex than that. But what is new here is that each of those languages has a formal semantics that is mechanized in Coq. And each of these arrows, each of those transformations is proved to be semantics preserving, again using the Coq proof assistant. And so in the end, when you compose everything, you get this theorem, which I wrote in Coq syntax, which says basically that for any program, C program P, if trans C program, which is the composition of all the passes, doesn't signal an error, but instead says, okay, and here is some TP, some transform program, which is in assembly. And then every observable behavior of this assembly program according to the assembly semantics is identical to one legal behavior of the C source code P according to the C semantics, or improves over one such behavior. So improving here means crashing less often or crashing later. Okay. And well, so it's a fairly big proof, but at least it can be broken naturally in independent proofs for every pass. And then there are some compilation patterns, some compilation verification patterns that can be used. So at the one hand, there's a verified transformation pattern where you formalize the transformation in Coq and then prove a theorem directly by reasoning on the transformation algorithm. And at the other extreme, there's so-called verified translation validation, where the transformation is performed by a piece of code that is completely untrusted and not verified. But at every run of the compiler, we feed the input and the output of this transformation into a validator, some kind of very specialized theorem prover, that tries to prove that they are semantically equivalent. And if it says yes, then compilation proceeds. If it says no, we do a compile time error. And the observation is that it suffices to prove the soundness of this validator, that if it says yes, the two inputs are actually semantically equivalent, to obtain soundness guarantees that are as strong as in this case, but often with less proof effort. And then there are mixed approaches where you can prove part of the transformation and then validate some other parts. So this is a fairly big proof, not as big as the CL4 though, about 100,000 lines of Coq. 15,000 lines are really source code. They are really the compilation algorithms. It took about 6 person-years, and well, if it is so big, it's also because there's low proof automation that could probably be improved. But an originality of CompCert is that it's programmed also in Coq. So we are using Coq not just as a logical framework for specifying and proving, but also as a programming language, because in the specification language, there's a small pure functional language where you can define functions that are recursive and proceed by case analysis on tree-shaped data, and that's all you need to write a compiler. Well, you need a little bit of imagination, like you need to use monads to handle errors and mutable state. You need to use purely functional data structures throughout. But the good thing about this approach is that you don't need a program logic. Okay, the compiler is an object of the Coq's logic and can be reasoned upon directly. And you're not losing in executability either, because there's an extraction mechanism in Coq that produces executable camel code from those specs. And so in the end, we can combine this camel code extracted from the proved part of the compiler with a few parts that are handwritten in camel. So some of them don't impact correctness because they are validated a posteriori. A few others remain to be proved, and a few even don't have any specification, so like pre-processing. And so in the end, we get a compiler that executes and can even be benchmarked for performance. That's what compiler writers do. And well, I'm not going over all these numbers, but the bottom line is that, well, CompCert is reasonably competitive with the GNU CC reference compiler, only 10 to 20% slower than GCC at first optimization level. So that's not great, but that's definitely acceptable. And the most important thing is, well, all this proof effort pays in quality. And so remember this team from the University of Utah that was breaking all compilers just by randomly generated C programs. Well, CompCert is basically the only compiler they could not break, even though they devoted about 6 CPU years to it. All right, so, well, let me conclude. Well, there are plenty of other stories that I would have liked to tell. For instance, well, in hardware verification, floating point algorithms in particular. In cryptography, some very nice work by Gilbert and colleagues at IMDEA Madrid on mechanizing cryptographic security proofs that are based on probabilistic reasoning over games, so non-trivial mathematics. But I'm a little out of time and you are a little tired. So let me conclude. Well, as those 3 examples show, proof assistance enable unprecedented scaling in many areas of computer science. And by scaling, I mean scaling in size and realism as the formal systems considered, but also scaling in assurance, okay, mathematical assurance. And there are additional side benefits. I think it makes research papers easier to write and more pleasant to read, just because, well, after you've labored on your mechanized formalization, you've really found the right definitions and all the key lemmas, and now you can just put that in the paper and tell the story of your proof instead of just telling your proof, okay, and that's much more interesting. In my experience, proof assistants also give a second chance to students who are insecure in their abilities to do mathematics on paper. And when I say students, I could also say engineers or even some fellow computer scientists. Because, okay, the proof assistant is stubborn, is stupid, and needs to be told everything 100 times. But it doesn't judge, okay? It's infinitely patient, it doesn't judge, not like an advisor, okay? So some students really like that. It also George mentioned that, I believe. It also facilitates collaborative work of the free software kind, okay, where you just put your proof on the web, and sometimes you get good feedback and even suggestions for improvement. Oh, here is, I took your proof and I added these 5 features. Maybe you're interested. Then there are also some risks or some points to keep in mind. One is that mechanized proofs do not eliminate all causes of errors. Okay? They just reduce the possible errors to the definitions and statements of the theorems. So you're pretty sure that you've proved it right, but did you prove the right thing? Okay? And so that's where you still need human reviewers and maybe even testing of specifications and that kind of things. Proof assistants are addictive and a huge time sink. Okay, so yeah, you will spend countless hours on that. And so if you're used to publishing 10 papers a year, maybe that's not the good approach. On the other hand, it's a time sink. Well, it's not a boring administrative meeting kind of time sink. Okay, it's more like an addictive video game kind of time sink. All right. I mean, it's about the same mixture of pleasure and frustration. So, so think of it this way. Rather than playing 2048, okay, you could be advancing science. Then, well, it should be apparent from George's talk, proper engineering of your specifications and proofs is crucial. I mean, if you just dive in the problem without giving some thought of, well, what are the key libraries I need, that would be a failure. Then an issue that was mentioned in Thomas Hale's talk is the fragmentation of the community around multiple theorem provers with very little interoperability between. Well, take my experience from the programming world. Okay, in the programming world, we also have dozens of programming languages, and yes, limited interoperability and some duplication of efforts between languages, but the world goes on, okay? So you have to admit to accept some amount of, well, duplicated work and implementation, but that's it. And finally, mechanized proofs, just like software, require maintenance and proper archival. I mean, new versions of proof assistance come and may change, maybe a little bit incompatible, and so you should update your proofs regularly. That may feel like a burden compared with just, you know, a mathematical journal that sits on a shelf. But on the other hand, well, it's certainly manageable, just like we do for software. Okay, so for more information on the 3 projects I presented, so here are some URLs, and my final words will be an exhortation. Go forth and mechanize. Thank you.
So, are there questions in the room?
I know you don't like this question, but a difference between Cell 4 and CompCert is that in Cell 4 there are some aspects of concurrency, and there are also systems like TLA Plus you didn't mention to study concurrency. Yeah. Do you think that the CoC approach you use would be usable by a Frenchman or Frenchwoman, to tackle this problem, or are there intrinsic
You mean
difficulty?
concurrency, semantics of concurrency, reasoning about concurrent programs?
Yeah, the kind of proof you need, the kind of logic which are a little bit different you need to, for example, in Cell 4 to prove things about concurrent, because the concurrency introduces new kind of bugs, basically, a new kind of difficulty.
That's absolutely
do you think this is tractable in the current status of this kind of technology?
I can think of several projects, for instance, where some separation logic was embedded into CoC and then could be used to reason about concurrent algorithms. So I agree with you that. And maybe you can also do some reasoning directly in CoC at a fairly abstract level of, just transition systems or whatever, where sequentiality and or concurrency are not as explicit. But yeah, I think that if you really want to verify some piece of concrete implementation that is concurrent, probably the first thing you need is a program logic, like a separation logic. Again, it can be embedded into CoC if you want. That's what Andrew Appel is doing at Princeton, for instance. Or you may want to use a specialized prover in this case. I think both options are open at this moment.
Okay. Any other question?
Do you have the impression that a lot of your manual proofs could be automated? And do you think it would be worth the effort?
Perhaps. So, yeah, I think there are kind of 2 levels of automatization that can be considered. So one is pretty basic. It's like, you have a big hypothesis involving big matches and lots of cases, and you want to invert that and get back to the few cases that don't contradict the hypothesis. So I think this can be automated in CoC even as of today. It's just that, I've been a little lazy. And then the next step of automation, would be, to perhaps more automatic handling of case analysis in general, but also in conclusions. Basically, the kind of things that automatic theorem provers for first-order logic can do. And yeah, at some point, I still put a lot of hope in integrating some of those SMT solvers as CoC tactics one way or another, even though I haven't tested the latest developments in this area.
Because your development is higher order at the top level, but then you very fast sink into first order reasoning.
That is true, yeah. So higher order reasoning is used in a few places, but is certainly not pervasive.
So any other question?
Yes. Concerning your program for generating prime numbers, you went a little bit fast, saying that you need Bertrand's postulate. Yes?
Oh, that's what Knut says in the answers to exercises.
Because Bertrand's postulate is a resultant density of prime number. That is, for every prime number, there is a bigger one that is less than the double. And here you need only the square.
Okay.
Okay? So it's a little arithmetic triviality, but it's not a triviality that you can get by pattern matching. So it raises an interesting problem on how to organize your library of mathematical developments, that you know which theorems are relevant See, it's not enough to have proven Bertrand theorem in your database, even though it's very long. Yes. You still need to find out that it's relevant, and you need a little bit of backward reasoning using arithmetic. So this is not just propositional reasoning.
Okay.
So that's a main problem, actually. It's how to organize our mathematical development in ways in which we can search automatically the relevant theorem.
Okay, good point.
Any other question in the audience? Okay, so let's thank the speaker again.